Alright, in the previous video we talked about how to handle this moment diagram that in some ways was a very simple moment diagram, second order, but boy, it had a lot of complicating pieces to it. And is there any way to decompose that into a simpler way? And in this particular instance the answer is yes, and it has a direct analogy to what's going on in the system. And that is, if we were to look at this beam as having a distributed load only over that middle span, and then a second case where that load is only over the cantilever, we get some much easier to work with results here. In that first case we get a nice symmetric parabola for the moment diagram, has WL squared over 8 for its maximum. We know where that centroid is at. It's going to be that 2/3 base times height for this area. Really easy and nice to work with. On this other one, what we're going to get is this little second order piece that's also going to be easy to work with because that slope out here is 0 at the far right. So that's going to be 1/3 base times height for that area with the centroid located at the 1/4, 3/4 point along this base. And then we got the triangle part, which is also going to be really easy to work with. That's absolutely a way that we could do this. Now note that mathematically what we're going to do is add those two cases together. When we're talking about structures, that adding together is not an associative property or anything like that. It's called superposition. We're just decomposing the whole into a sum of its linear parts. Right? And so note here, we've got the big curve that comes WL squared over 8 from that middle load, and then we've got this little triangular and then second order part. And when we add those two pieces together, of course at any one given distance x, we add the two values together to get to the total. So at the far left, that would be 0 and 0, giving us 0. At the far right, again, it'd be 0 for each loading effect, and we still get back to 0. At this middle support, well, one of them has 0, the other has -6, so we add those together, we get to -6. And of course, everywhere out in the right hand portion, you know, we don't have any effect from that one load, so okay, that just gets transferred over. So now it's just this piece that's right here. Right, so let's go to the middle point here. In the middle point, that WL squared over 8 was 13.5 kip foot. And then because we're halfway along and it's a linear variation from this -6 to 0, that of course means -3. Right? And so if we take 13.5 minus 3, then right at the middle of that span, the moment is 10.5 kip foot, not actually the maximum. The maximum we know occurs where the shear is 0, which is at the 13.33 foot distance. Right? I don't have that marked. Well, I guess I have it marked right down here. Right? So that's where the shear was 0. So if you go in and look at the scaling, linear scaling on this one, you get -2.67. And if you come into the second order curve on this other one, right, for instance, and the way I would actually do it, since I know where that location is, I'm going to go and just do a free body diagram and calculate what the moment is there just due from this load only, and that would be the 13.33. Add those two together and we get a 10.67, which is the actual maximum located at that 13.33 portion. Because this is all symmetric, then this flips over another 13.33 to get to moment equal to 0, and then we have another 3.33 feet to get to the support. That's another way that we could work with these moment diagrams for the moment area calculations, because again, this will be a lot easier to work with, right? These two pieces, then that decomposing all these other little pieces into their various segments and getting the moment arms right and all that sort of thing.